Hello and welcome to this union medal lecture, I should say. My name is Hans Thybo. I'm the president of the EDU, and I'm very pleased to see all of you here for this exciting lecture. I suppose you are aware that the Cassini medal is one of the most prestigious awards that are being given by the EDU. There are 3 union medals, and Cassini medal is one of these. And to receive these union medals also imply that the recipient is becoming an honorary member of EDU. And I'm very pleased. I'll not talk for long. You came here to listen to Jonathan Lunine, and I'll just read aloud the short version of the citation for his medal. Jonathan Lunine received the Jean-Dominique Cassini Medal for his key discoveries and his seminal contributions in planetary sciences and exobiology, his leadership and instrumental participation in the design and implementation of space exploration missions, and his pivotal role in space science policy. And I suppose that what we will hear now is a review of all these exciting subjects. So please, Jonathan Lunine, the stage is yours.
Very good. So thank you very much, Mr. President. And I want to again thank the Council, the committee members, the leadership of the EGU for this wonderful recognition and the wonderful week that my wife Cynthia and I have had here in Vienna, which of course we all know is an incredibly wonderful city. And so thank you again. What I want to do is a few things. I am going to get to the subject of this talk as promised in the title, which is laying out the case that there are 2 habitable worlds in the Saturn system and that we should go back and explore them. But I actually want to start with a little bit of history, and it's personal history on how I came to be involved in Cassini. And I actually want this clock to run, so does anyone know how that works? I push something. Okay, you know what, don't worry about it. I'll use that clock over there, but it was convenient. That's okay. I want to talk a little bit about how I came to be involved in Cassini, because it illustrates very well the contingent nature, thank you, of I think all of our careers, and the fact that we don't always do what we expected we would do. And this, of course, has been for me a tremendous opportunity. And then I want to talk quite a bit about Titan and the discoveries that Cassini-Huygens has made for 2 reasons. One is that I find people are a lot less familiar with Titan and why it's important from an astrobiological point of view, and to do that you have to explain what Cassini has discovered. And secondly, I want to lay out the case that Cassini quite possibly has been the most successful and most remarkable planetary mission that humankind has ever mounted, robotic missions. So that's what I will do in this talk, and all in 45 minutes. If I hold this the right way. Perfect. So when I went to college, I was an astronomy major. I imagined that I would become an astronomer of some variety. I took a lot of astronomy courses. I thought about planetary exploration. It fascinated me as a kid, but I actually hadn't thought about that specifically as a career. I did, however, have a subscription to Sky and Telescope magazine, which many of you are aware of, many others may not be. But unfortunately, this picture is very fuzzy because I took it off of eBay. And I received this issue of Sky and Telescope in March of 1979 when I was a junior at the University of Rochester. And it totally stunned me. What stunned me was the cover picture, and here it is a lot clearer. And it was an approach picture taken by Voyager 1 of Jupiter and one of its moons, Io. And when I took this magazine out of its wrapper, looking at the detail that was present in this image absolutely stunned me. I mean, absolutely stunned me. I couldn't imagine that Jupiter would have that kind of detail and that little Io over here would be so strange. Of course, it turned out to be very strange, turned out to be volcanic. And at that point, I decided to apply for graduate programs in planetary science. And so that changed the direction of my career. I ended up at the Division of Geological and Planetary Science at the California Institute of Technology for graduate school. And that's where the planetary science program was. I was working for David Stevenson, who actually did his PhD at Cornell some years before. And he had just arrived at Caltech as well as an assistant or associate professor. So we started working on problems related to the origin of the moons of Jupiter, and we did get one paper out of it, although the bulk of what I was supposed to do got done within a few months by a group in Japan, and they sent us the paper, and it was all over with, basically. So right around the same time, Voyager 1 flew through the Saturn system and flew by Titan, and discovered, in fact, that this moon had not only methane, but as correctly predicted by Don Hunton and a few others, and models that were worked on by Sushila Treya, there was molecular nitrogen in the atmosphere. That was the bulk of the atmosphere. And so it had a high surface pressure, as Don Hunton had predicted. It had a greenhouse effect, substantial greenhouse effect. And because the atmosphere is so thick, there was a lot of methane in it. Even though methane is only a few percent of the mixing ratio of the atmosphere, that's a lot of methane. And yet, paradoxically, it's not enough methane to supply Titan's atmosphere, given the fact that methane is photolized by ultraviolet light. It's not enough to maintain methane in the atmosphere for billions of years. In fact, it's only enough to sustain about 30 million years worth of methane photochemistry. So immediately the question arose, what was the source of methane in Titan's atmosphere? Now, there had been models that had been done by Carl Sagan, Stan Dermott, proposing methane oceans on Titan. The problem with the methane ocean idea, as pointed out by Mike Flaser, is that given the conditions on Titan, if there were large-scale seas or oceans of methane, that the relative humidity of methane near the surface should be close to 100%, and it wasn't. It was, based on Voyager data, about 50%. So with my advisor Dave Stevenson and Yuk Jung, who had worked out a detailed photochemical model, which was really a descendant of work by Darrell Strobel, who in the late 70s had essentially sketched out the photochemistry, we considered the products of the methane chemistry. And again, as sketched out really first by Darrell, there are two methane molecules photolized by ultraviolet light in the upper atmosphere, get converted to both ethane and acetylene. And the reason that those are relatively abundant is that the hydrogen that's liberated from the methane in order to produce these other species is lost to space because of Titan's low gravity. And indeed, Voyager 1 actually, with its ultraviolet spectrometer, imaged the corona of hydrogen around Titan and confirmed that this was what was happening. So the methane chemistry in the upper atmosphere is irreversible. The methane is destroyed, and the products, because of the very cold temperatures at the base of the stratosphere of Titan, as revealed by Voyager 1, that all sediments out to the surface. So what we considered was the physical chemistry of these species, and we realized that in particular, here's nitrogen coming in, so hydrogen cyanide is an important player as well. But what we realized was that ethane and methane both, because they mix so well in equilibrium, would form an ocean not of pure methane, but of ethane-methane. And the methane relative humidity then is simply a reflection of the ratio of methane to the total methane plus ethane in the ocean. We also realized that the nitrogen in the atmosphere would dissolve significantly in this ocean. At the pressures measured by Voyager, 1.5 atmospheres, and the temperature of 94 Kelvin at the equator, there should be about 17 or 18% nitrogen relative to methane if it's a pure methane ocean, and about 10% if it's a 50-50 mixture. So over time, nitrogen is actually exsolving from this ocean system, which is losing volume because 2 methane molecules are required to produce an ethane. So this ocean becomes both the source of methane supplied to the upper atmosphere and the sink of all of the methane photolysis that's going on, the primary sink, because indeed these photochemical models predicted that ethane would be far and away the most abundant product of the methane chemistry. So we wrote this up, published it in Science. It got quite a lot of press and became a centerpiece of my dissertation. And then coincidentally and very fortunately, right around the time that we were writing this up, the first plans were being hatched for what would become the Cassini-Huygens mission. And so this is some text taken from a 1986 National Academy, National Research Council, European Science Foundation report on cooperation between the United States and what at the time was called Western Europe, cooperation in planetary exploration. So this reads in part that in November of 1982, a group of 29 European scientists submitted a proposal for a Saturn orbiter and Titan probe mission to be conducted jointly with NASA. And the two principal individuals in Europe who submitted this proposal, the leaders of the group, were Daniel Gautier and Wing Ip. And Wing is here today, and Danielle is in Paris. The text contained a comprehensive summary of the significant scientific issues that were still remaining after the Voyager flybys, and the proposal, which was called the Cassini proposal, showed conclusively that a Saturn orbiter with a Titan radar mapper, together with a Titan atmospheric probe, one that was not designed to land on the surface, would be needed to provide answers to these important questions. Now, part of this group came to JPL in what I think was late 83 or 84, and I was still at Caltech. The paper had been published. And they asked David Stevenson to give a presentation on the current state of knowledge of Titan's surface. And here again was another contingent moment for me, which is that Dave, rather than going and giving this talk, said that they ought to have this graduate student of his give the talk, and that was me. So I became introduced to the people on this list, and it was Dave Stevenson who made that possible. Shortly after that, I was hired by Don Hunton, who was playing a key role as well in the development of this mission at the University of Arizona. He hired me as a postdoc, and he got me plugged into the Saturn and Titan atmosphere community. Charles Alachi had invited me to JPL to be part of a think tank group on what one could actually do with a Titan radar. And Angeletta Corradini, who had started an institute in Rome in planetary science years before, had been on this committee and invited me then to participate in a meeting in Vulcano, Italy in 1985 on the subject of the satellites, the outer solar system. So these four relatively senior individuals really got me plugged into studies leading up to the Cassini mission. And one example that I retrieved from an old folder was a white paper that I had prepared, 1987, for what was called the Cassini Surface Science Workshop, where I went through the straw man payload that had been talked about for the probe, which was not called the Huygens probe, it was called the Cassini probe, to demonstrate that you could, from measurements during the descent of the probe, learn a lot about the surface of Titan. And so there were a number of studies being done over a number of years. I also found this in my folder, which was a graph prepared by a graduate student at the University of Arizona, Bashar Risk, comparing the solubility of nitrogen in two different studies, one that I had done after my thesis, and the other Reed Thompson at Cornell University. And we went ahead and started doing models of how this global ocean would evolve with time. Bashar went on to play a key role in the imaging system on the Huygens probe. Now, of course, the ocean went away. Radar data pretty soon after my dissertation, and thankfully not before I defended, showed that most of the surface was actually solid, and so the question came up again, where the heck was all the methane? Where did it come from? Where did the methane come from? But anyway, meanwhile, through the heroic efforts of Gautier, of IP in the United States, they had a third partner, Toby Owen. The three of them are considered the fathers of Cassini, along with Don Hunton and a number of other scientists, really pushed for this mission at NASA and ESA. And they succeeded. And so this is the newsletter from 1988 announcing that the ESA Science Program Committee selected the Cassini mission as the next medium-sized ESA science project. And furthermore, that the probe, while the orbiter would be named Cassini after Jean-Dominique Cassini or Giovanni Domenico Cassini, depending on which stage of his life, or even Gian Domenico Cassini, because he changed his name twice. The probe itself would be named after Christiaan Huygens, the Dutch astronomer who discovered Titan. This mission was lobbied for successfully in Europe. It was lobbied successfully in the United States. This particular picture taken, I believe, Wing, at the 10th anniversary, correct me if I'm wrong, but it was taken many years later. You see here Wing Ip, you see Danielle Gautier, you see Toby Owen, you see the first project scientist for the US side for the Cassini orbiter, Dennis Matson, and the Huygens project scientist, Jean-Pierre Le Breton. You also see this gentleman, George Schoon, who worked for ESA and was an engineer and was essentially the individual with a small team who demonstrated that Europe could actually build and design a probe that would do all of the science objectives required for this mission. And this actually made it possible to conceive of this as an international mission, because prior to this, there was considerable uncertainty as to whether ESA would be ready to build a probe like this. There were concepts from NASA Ames and Hughes Aircraft and others showing that they could build a probe. Their concepts actually didn't satisfy the strongman science objectives, but the concept that George put together did. And that established this relationship where ESA had responsibility for the probe, the United States had responsibility for the orbiter. The first meeting of the Cassini Project Science Group after the announcements of opportunity, the proposal writing, and so on, took place in December of 1990 at JPL. This is part of the agenda. You see I had my 10 minutes here, having applied to be the interdisciplinary scientist for Titan surface and atmosphere. I was selected and I had my 10 minutes to explain what I thought I was going to do. It's notable that in January of this year, the Cassini project held its 65th Project Science Group meeting. And if you take account of the fact that these occur about 3 times a year, you can pretty much do the math and realize how long this mission has been going on. It's had remarkable longevity, but more importantly, remarkable success on the science side. So I want to move now to talking specifically about Titan. And as I mentioned, the ocean had gone away, and I feel really guilty about this because one of the instruments selected, Surface Science Package, had all these features designed to measure the composition of the liquid and various other things, but it did a lot of other really great stuff, as you'll see in a bit. This is a figure that was published in 1997 in a paper that I wrote. It's actually based on some work that I had done and also work that Ralph Lorenz, who started out as an engineer at ESTEC and decided to go into science and got his PhD at Kent, came to the University of Arizona as a postdoc for Peter Smith and myself, and we ended up working together. In the end, he spent most of his time working with me. And the reason I chose this picture of Ralph with the Buddha is to give you a sense of where all the wisdom and intelligence was in this. I really have learned a lot more from Ralph than I think Ralph has learned from me, but it's been a tremendous and long-lasting collaboration. So you actually see in this 1997 figure, which we drew the year of the Cassini launch, you see a lot of things that actually, in the end, were discovered by Cassini and Huygens. There are seas and lakes, but they're restricted to the northern hemisphere. Impacts do cause surface chemistry, and actually there's some work now that's been done that suggests that this really is the case, that we're beginning to see this with Cassini. Cassini has observed moist convection in Titan's atmosphere, and I'll get to that in a minute, and Cassini has observed these dunes, and in fact there was just a paper by Ben Charnay in Paris who has put together a model based on his global circulation model showing that methane rainstorms might in fact play a key role in forming the longitudinal dunes that occupy 20% of Titan's surface. These are solid organics that are deposited on the surface. Some things that we haven't seen are evidence for these flows of ammonia water. There's really very little evidence for water or ammonia-based volcanism on the surface of Titan, but the Huygens probe has seen argon-40 as well as the Cassini orbiter, both through mass spectrometers. And of course, everything does sediment out, as was worked out many years before by the people I've mentioned, Strobel and Hunton and so on. So this was just to illustrate that we expected a complex surface, and it required all of the complexity of Cassini itself to really be able to tease this out. This is probably the most, or at least one of the most capable planetary spacecraft ever built. And again, the European Space Agency had primary responsibility for the Huygens probe, the United States primary responsibility for the Cassini orbiter. The communications system on the orbiter was jointly built with the Italian Space Agency, OSI, and then all the instruments, and I keep forgetting 12 or 13 or 14 on the orbiter, depending on how you parse them, and 6 on the Huygens probe, were all international instruments. Every one of them had components and individuals from both Europe and the United States. So this was an incredibly complex undertaking, incredibly successful. We would not have any of this today if this were left alone to the United States, because as many of you know, a couple of years before launch, or a few years before, the NASA administrator at the time, whose name I shall not quote, basically managed to convince Congress to cancel this thing. And so Roger Bonnet, who was head of science at ESA, convinced the Director General, as I understand it. The Director General sent a letter directly to Congress indicating that if Cassini-Huygens were canceled, that ESA would reevaluate all its international commitments, which meant the space station, of course. And lo and behold, there it is. Okay, so it launched, it got there. You know, there's a lot to talk about, but I'm only going to try to lead you through the arguments as to why Titan is so complex and so interesting. The first indication that it was came from the Huygens probe. And in particular, these images taken by the Huygens probe, by the descent imager spectral radiometer, the PI for which was Marty Tomasco at the University of Arizona, shown here with Larry Soderblom, another IDS, myself, Laura Defoe, and Sylvain Doutet, part of their team, showed these fluvial features, and in fact showed them in stereo because of the trajectory that the probe flew on its parachute over those features. These are about 10 meters or so across. The branching follows the topography very well. There's another area on the side of this elevated terrain that's mostly fracture that may be filled with liquid as well, and the Huygens probe landed somewhere down in here in this flat area, which turns out to be full of rounded rocks, rounded pebbles, which are probably ice and organics. But what's remarkable is that the Huygens probe was so well instrumented, in spite of the fact that it was the first probe to land in the outer solar system, on a moon of the outer solar system. And remember, the pressure here at the surface is 1.5 atmospheres. So this is the second densest atmosphere, if you work out the density, of any of the solid bodies in the solar system, denser than the Earth's atmosphere at the surface. So the Huygens probe had multiple indications of the meteorology being the result of methane as the working fluid. And one of them, in addition to these geologic features, hydrologic features, is the data from the gas chromatograph mass spectrometer. This was an instrument led by Hasso Niemann at Goddard. And what you see is mole fraction of methane versus time during descent. The landing is shown here. And you see the methane abundance increasing as the altitude of the probe decreases. And then the methane abundance becomes constant. So this is the base of the cloud at about 7 or 8 kilometers altitude, and that's fully consistent with the calculation of the temperature profile and the lifting condensation level. That's where you expect the methane cloud to be. And in fact, some years before that, a master's degree student at Arizona in meteorology, Maria Ewald, calculated the cloud base and the convective potential in Titan's atmosphere and did a simple entraining plume model of methane thunderstorms to show that they really would go. So for 5%, the cloud base is at about 9 kilometers in our model, and we get positive lift up potentially to 20 kilometers. So rainstorms are possible. And of course, this was a very simple and crude model, but it was, as far as I know, the earliest. And then Cassini, here's the Huygens data, but the Cassini orbiter got in the act because in 2010, at the time that equinox arrived in the Saturn system, and the seasons, by the way, are 7 years long. The orbit of Saturn is 29.5 years, so seasons come slowly. But this is equinox, and this area that previously was rather bright, as seen in the Cassini camera, after these clouds, and this is sort of the remnant of those clouds, had formed and passed over this area, much of this became very dark, and then gradually brightened again over a period of several months. So this was a good indication of rainfall, wetting of the surface, and then drying again, and this has to be methane. And I must point out to you that the Cassini orbiter is an orbiter of Saturn, not of Titan. So these observations of Titan are taken on flybys, and we don't have continuous coverage. So to be able to observe this on multiple passes is a credit to the imaging team, led by Carolyn Porco, and this particular investigation led by Elizabeth Turtle at the Applied Physics Lab, Johns Hopkins. And then on the surface, the evidence for fluvial erosion, tumbling of these pebbles that are several centimeters across. These are probably ice and organics, although we don't really know for sure. Eric Karkowska, who is a member of the DISR camera team, Descent Imager Spectral Radiometer, has done an enormous amount of work to try to understand what's going on in these images. This is a lamp that was used to make spectra of the surface because light on Titan is mostly in the red. The aerosols in the atmosphere scatter out the blue part of the spectrum. He determined that this feature is real, that it's a methane dewdrop on the edge of the probe. So these are images taken at different times after landing. And I want to emphasize that when this project started, the Huygens probe was going to be an atmospheric probe with no guarantee of data from the surface. And in fact, over an hour of data was recovered from the surface, including these data, accelerometry data from the surface science and the HASI packages, measurements of the electric field from the surface, measurements of methane and carbon dioxide and other species evaporating from the soil and being measured directly by the mass spectrometer, and then measurements of the thermal conductivity. So a broad suite of measurements were taken that suggest that this really is a kind of deflated lake bed with rounded pebbles and lots of methane and other species hiding in the surface, possibly, as we heard yesterday from Eric, underneath a somewhat dry, hard layer. So there is methane in the methane cycle. We know that directly thanks to Huygens and Cassini, and we also know that there are lakes and seas in this northern hemisphere region and a couple of lakes in the southern hemisphere. We know that thanks to the several instruments, initially the imaging system that photographed Ontario Locus in the southern hemisphere. But for these northern lakes, which were in the dark when they were discovered, it was the Cassini radar system, which was a joint facility instrument of OSI, the Italian Space Agency, and JPL. And what you see here is a composite image. The radar makes its measurements in strips using the main antenna, And you see this pattern of dark features with a very high level of contrast relative to the brighter surroundings. So these are smooth because the way the radar makes its images, it sends a radio signal off to the side, not looking straight down. And so anything that is really smooth will look very, very dark. Now, for a long time after these were discovered with the radar data, beginning in 2006, every talk about the seas of Titan involved a several-minute dissertation on why the speaker, whoever that was, thought that these were really liquid, because the radar system didn't sample the liquids directly. But in Rome, at the University of Rome, La Sapienza, graduate student Marco Mastrogiuseppe, working for several people, including Enrico Flamini, another student, Valerio Paggiali, were working on Mars data and had worked out routines to recover secondary bounces from Mars-sounding radar. And this is Marco in this picture, and he led the effort to apply the same technique to the Cassini radar data. Now not looking off to the side, but looking straight down in what's called altimetry mode. And this was done over one of the large seas of Titan called Ligeia Mare, which is about the size, it's about 140,000 square kilometers, but it's about the size of Lake Superior in North America. And the concept here is Cassini sends a signal down, and there's a bounce off the top of this dark stuff, whatever that is, but you look for a secondary bounce off of another layer at the bottom, and if this is a body of liquid, that second bounce should be at the interface between the liquid and the ground underneath. And indeed, this is a difficult measurement to make, even though methane and ethane are relatively transparent at 2 centimeter wavelength. There's still all sorts of things one has to contend with. There are aliasing problems and so on and so forth from the radar, which has, for an imaging radar, a relatively small antenna, 3 meters. So that group worked all this out, and the result was what you see down here. This is the traverse across a radar image of part of Ligeia Mare. This is the bounce off the top. This is time in microseconds versus latitude along here. This that you see here, this bowl-shaped signal, is the secondary bounce off of a bottom. And this is the power level in decibels that you see here. So this time delay corresponds to about 160 meters in depth. So this radio signal is passing through over 300 meters of liquid, and yet is still visible, even though it's rather weak in here. And it's actually remarkably strong. Over several hundred meters means that this liquid has to be much more transparent than almost anything we think of as liquid. Liquid CO2, liquid water, liquid ammonia, whatever. It's consistent with liquid methane, possibly liquid ethane, based on what has been measured and reported in the literature. Now, in fact, these results were so exciting, as reported here in GRL, that they were paired with some work that had actually begun a little bit before the work of Marco and colleagues had been started. This was experimental work at JPL led by Carl Mitchell and Marty Barmatz, who found a clever way to measure these very, very low absorption, very transparent liquids. So they got quantitative data on what's called the loss tangent at the Cassini radar wavelengths for a variety of species. And indeed, the transparency of this body of liquid, Ligeia Mare, is so great that this must mostly be liquid methane. So the number that comes out of these two papers is 80% methane, about 5% ethane, and 15% nitrogen. The nitrogen number comes essentially from that graph that I showed you early in the talk that Bashar Risk had worked on, or numbers like that. It's the solubility of nitrogen. Once one has established the ratio of the methane to ethane in these seas, because they are open systems exposed to the nitrogen, then the nitrogen solubility is determined. So with the absorption numbers, you also get the nitrogen number based on its known solubility. And so this is the mixture that we came up with. It's actually going to be revised to a somewhat less methane-rich value in a few months based on some reanalysis by Marco. But basically, we know from Cassini that these are ethane, methane, nitrogen Cs. And we know it essentially directly. This is as direct as you can do from a flyby spacecraft, and it's a good quantitative measurement that's been done, and something that was never predicted Cassini would ever be able to do. So Marco is now a postdoc, a research associate at Cornell University, and working on the other Cs as well. Now, the result of the depth measurements and the area that you see here the result of that actually was presaged a bit by some work that Ralph Lorenz had done estimating the depth. But the depth, as we know now from Ligeia Mare, and the depth that we actually have from Punga Mare that we'll be reporting soon, and the lower limit to the depth from Kraken, which appears to be too deep to get a bottom signal, one can conclude that there's about 250 times more hydrocarbon in these seas on Titan than in all the known oil and gas reserves on the Earth. And as soon as that GRL paper came out, gas prices began to fall, as you know, worldwide. And this is actually the reason for that. So, but this is still not enough to supply the methane in Titan's atmosphere. In fact, this is a lot less than the methane in Titan's atmosphere. This is not the reservoir. And so the reservoir is still yet to be determined. The seas are variable. One of the surprises from Cassini is that repeated radar studies have shown, as we've moved now into northern spring and the sun is rising higher in the sky and these seas are getting heated up, and based on global circulation models, the winds are increasing. As Alex Hayes, an assistant professor at Cornell and a member of the radar team, had predicted, along with a large cohort of people in a paper a couple of years ago, we should begin to see features on these seas. And in fact, Cassini does begin to see features. Here's one that appeared along the edge of a peninsula. This feature did not appear, was not present prior to the T92 flyby a couple of years ago. And it was still present earlier, I guess late in 2014, in the T104 flyby shown here, and then in the T108 flyby, I'm not going to explain these numbers because they're not important, which was more recent, that feature's gone away completely. So there are transient features, there are things happening in these seas that are time variable on a short term, and some of it may be waves, some of it may be deposition of material off of, for example, this peninsula. All these possibilities are being evaluated by the radar team and also by the VIMS team, which has data. This is the near-infrared mapping spectrometer, which also observes the seas. And this work is being led by Jason Hofgardner, who's a graduate student at Cornell. But between the radar data and the VIMS data, we're starting to get a good picture of the behavior of these seas. And I should add that VIMS has contributed to the composition by measuring the absorption, the actual presence in an absorption feature of ethane in a couple of bodies of liquid on Titan. So we have multi-wavelength data that demonstrates this. Now, the interior of Titan is important in terms of establishing potential for habitability. And Titan's a large body. It's the second largest moon in the solar system. It is slightly smaller than the moon Ganymede, but it's large enough and has a density high enough, suggesting that it's 60% rock and 40% ice, that there are substantial internal sources of heat in this body. But we did not know before Cassini how the mass was distributed in the interior. The expectation was that with the large amount of rock and radiogenic heating, radioactive decay, the Titan should be fully differentiated like Ganymede. It should have a rocky core and an ice layer outside. Well, that's nearly the case, but not quite. It's a little bit more complicated. First of all, the radio science system on Cassini can be used to measure the mass distribution in the moons as Cassini flies by each of these moons in the Saturn system. And Titan's a great target because it's so large. But it's a difficult target because it has an atmosphere, and if you try to fly Cassini too close to Titan, atmospheric drag affects the measurements. So Luciano Yes, who's a professor at La Sapienza, and his group in Rome have been the leaders in teasing out from these measurements effectively of the change in radial velocity of Cassini as measured by the Doppler shift of the transmitter, the mass distribution in Titan and other bodies in the Saturn system. And what they've come up with is that Titan is not fully differentiated. It has a higher moment of inertia than Ganymede does. At the same time, they've been able, based on a paper by Nicole Rappaport and others prior to the arrival of Cassini at Saturn, they've been able to use the predicted tidal distortion of Titan by Saturn at its farthest distance from Saturn and its closest distance, the orbit is slightly eccentric, to determine what's called the tidal love number of Titan. And that, as published in 2000 and, whoops, I don't have it on here, but it's 2012 or 13, Luciano, that is a surprisingly high number. Titan is very deformable. Essentially, it's squishy, and it's also, essentially from the moment of inertia data, bloated. And when you put those two things together, the most self-consistent model with the geophysics is that yes, Titan has a rocky core, and indeed probably a metallic core inside of that, but the rock is hydrated. It's hydrous silicate. And what that allows is, even though the density of the rock is lower, the volume that the rock occupies is much larger, and that increases the moment of inertia. The tidal love number, the high value of that, 0.6, is actually higher, significantly higher than a pure liquid water ocean lying under a thin ice crust. The deformation of Titan would require that there be a liquid water ocean so that the crust that we see, the shell essentially, then is decoupled from the interior. But the remarkable thing about the value of the tidal love number is that this ocean must be essentially higher in density, or is likely to be higher in density than liquid water, perhaps by 10 or 20%, which means that it has salts and other minerals dissolved in it. So a few years ago, Gabriel Tobey, these are both former students of Christophe Sautin, who's done a lot of work on the geophysics of Titan, and we both had a chance to work with both of these individuals on Cassini data. And so Gabriel Tobey a few years ago led a paper in which we proposed that Titan had remained warm because the crust of Titan is loaded with methane clathrate hydrate, which has a lower thermal conductivity and a higher rigidity than normal water ice. That makes it easy to maintain a liquid water ocean in Titan's interior without having a lot of ammonia. And we have evidence that there's not a lot of ammonia in Titan's interior. There's some, but possibly only a few percent overall. So with this clathrate hydrate layer, Julie Castillo-Roget, who's at JPL now, led an effort to produce a model in which Titan has this hydrated silicate interior, and with the clathrate ice remains warm enough that the ocean itself is not underlain by high pressure ice, which was the traditional model for Titan, but in fact is at least partially in direct contact with the hydrous silicate, which allows for these minerals to be leached into the ocean, is probably why we see lots of argon-40 as well in Titan's atmosphere, which is a decay product of potassium. And of course, this immediately tells you that this could be a habitable environment. So if we add clathrate hydrate to the crust, this not only keeps the interior warm, but this provides a ready mechanism for resupplying methane in the atmosphere. And some recent work by Christophe Sautin and Matthew Chokran has laid out how that might occur. So we have this extraordinary picture of Titan, and in the last 5 to 10 minutes, I want to apply this picture to its potential for habitability. And there are several obvious places to look on Titan, both for prebiotic processes and also possibly for biotic processes. So Titan is organic rich. It has a lot of organics in the atmosphere. The methane and the nitrogen in the atmosphere are photolyzed and produce products that rain out on the surface. Methane is a working meteorological fluid that runs along the surface, pushes some material to the poles. Wind shapes some of the organics into dunes. There are a lot of ways to alter the organics on the surface, but underneath all of this is this liquid water ocean, which is laden with minerals. And so obviously, you can imagine that this might be a place where at the interface with the rock, there are hydrothermal vents. The problem, though, is that the crust is 40, 50 kilometers thick. This was actually determined in another way by the Huygens probe, which measured the electric field of Titan, and as described by Jean-Pierre Le Breton yesterday, one can make good arguments that the measured electric field enclosed in a cavity is actually bounded at the bottom by a high electrical conductivity liquid, namely salty liquid water. So this crust is hard to penetrate. We're not going to sample the ocean. The only place we might be able to find traces of whatever organic chemistry is going on in the ocean is by looking at places where impacts or cryovolcanism has brought this material to the surface. And that's going to be difficult to do, but possible some days. What I'm more interested in is the possibility that there is a very exotic form of life existing in the ethane-methane liquids. It would be a totally alien biology. It would require very different biochemistry. But even looking for this and finding evidence of self-organizing chemistry would be a strong test of the idea that the evolution of complexity, including chemical complexity in the cosmos, is such a strong part of the overall evolution of the cosmos that it occurs in whatever basic liquids and energy-rich environments are available. And one of those is the ethane-methane seas of Titan. So there's some evidence for surface chemistry from VIMS, and this is the visible imaging mapping spectrometer on the orbiter, and from the mass spectrometer on the Huygens probe. For example, we know these four species, ethane, methane, acetylene, and hydrogen cyanide, exist in the atmosphere, and we know that ethane and methane exist in the seas, but we see very little acetylene and hydrogen cyanide, which are the two dominant solid products of methane, on the shores on the solid part of Titan. And instead, we see cyanoacetylene and acetonitrile, which says the chemistry is occurring on the surface as well as in the atmosphere. So there's been some work recently, and I think this is a field for young people, by two very young scientists, Lucy Norman, who just got her PhD at Leeds and is now at the University of Hong Kong, showing that you could construct vesicle structures in hydrocarbons using phosphates and other compounds that may or may not be present. James Stevenson at Cornell constructed this virus-sized structure out of purely hydrogen cyanide put together in the form of different polymers. Now, do these actually form? We don't know. But you can look for this stuff in the seas. And the way you look for it was shown by Melissa Traynor, who's a mass spectroscopist, spectrometrist at Goddard, who modeled a sort of an imaginary Titan mass spectrum that you would get from the lakes and seas of Titan. The black on this mass spectrum, this is relative intensity versus mass. The black is the dominant constituents in the seas, the ethane and the methane. The red that she's put in is a simulation of the mass spectrum that you would get from the airfall of all of these organic aerosols that fall out from the atmosphere. And then if you imagine the chemistry in these seas of Titan, these methane-ethane seas, has progressed to the point where polymers of HCN are being built up to make structures, and this would be a starting point. If you have this structure at a part per million in the seas, that would give you the signature shown in the blue. And this is actually a fragmentation pattern that she calculated for this molecule. So if you land on the seas of Titan with a modern mass spectrometer, you can look for evidence that the chemistry in the seas is evolving toward a level of complexity that we would call life. And in fact, this was proposed as a NASA Discovery mission, Titan Mare Explorer. Ellen Stofan was the PI, Ralph Lorenz was the project scientist, and I was the deputy PI. NASA said no for various reasons that are not worth talking about here, but we nearly made it. It should be pointed out that we can't simply propose this time after time, no pun intended, because in the previous proposal cycle, we would have landed in Ligeia Mare at a time when the sun and the Earth, right next to it, were just 20 degrees above the horizon. That's just enough to be able to communicate with the spacecraft. If we were approved today and flew to Titan, the Earth and the sun would be, because of the seasonal changes, would be down here. The arrival, I remind you, would be in the 2020s. And we could not communicate with the Earth. So the next opportunity to do this mission as a standalone probe is when I'm 90 years old or something like that. Anyway, it's great. Athena Koustenis has been pushing very hard for many years in Europe and the United States for a flagship mission to Titan, and because time didn't make it, something like this may well be the way that we will learn about the seas of Titan, with an orbiter that allows for a relay to the probe, and then you can go anytime you want. And so Athena played a key role in a study of the Titan Saturn system mission that was done between the United States and Europe, between JPL and STEC. I was involved as well. Kim Ray here led the effort in the US side. But Athena's been pushing this, and she is so effective in European planetary science politics that I know someday she's going to prevail. I just hope it's while I'm young enough to still care about it. So if we can't go to Titan, let me talk in the last 5 minutes about another body in the Saturn system that I have not dwelled on, but I think most of you have heard about, and that's Saturn's moon Enceladus, which is actually about 1,000 times smaller than Titan in size. It has no atmosphere, but what Cassini discovered, remarkably, is that it has an active plume of material that is coming out of the South Pole, spewed out into Saturn orbit, forms the E-ring, which has been known now since Voyager days or before, and that plume is coming out of these south polar fractures on this moon that's only 500 kilometers across. And in fact, if you look close up, the plume, underneath the plume, the source is a series of jets, maybe as many as 100, coming out of this fracture system at the South Pole. Enceladus is somewhat tidally heated. It's not quite understood the amount of energy that's coming out. It has some interactions with Saturn's moon Dione, but there's strong evidence that this plume is long-lived and has been around certainly for centuries and maybe longer. In that plume, as measured by the Cassini ion neutral mass spectrometer, for which Hunter Wade is the PI, not only is water found, which is what you expect because this is an icy moon, but organics, methane, simple organics, carbon dioxide, and some complex organics as well, and nitrogen. And from the Cosmic Dust Analyzer, CDA on Cassini, Frank Postberg and Ralph Srama, Cassini has found sodium and potassium at such a level in the larger ice particles that this is very strong evidence that those ice particles are frozen seawater. Cassini has found silicon nanograins, as shown by the CDA team in a recent paper, the chemistry of which argues that there are hydrothermal systems somewhere in the interior. And there is a high heat flow from the South Polar region. But the radio science team, led by Luciano Yes, in a very difficult analysis, because Enceladus is so small, have been able to show that there is a substantial body of liquid, maybe global, but at least regional out to 40 degrees from the South Pole. So there is a long-lived body of liquid water. And this is one of the most remarkable stories from the Cassini mission, that these multiple instruments over many disciplines have one by one come up with the same result, which is that this is a habitable environment. It has a large salty ocean, it has organics, it has hydrothermal systems and energy, and most importantly, you get free samples because the stuff is spewing out into space. You don't need a lander, you don't need a drill or a penetrator, you just fly through the plume the way that Cassini has done. And the last flyby for Cassini is this October, but Cassini's mass spectrometer and the CDA are limited in their mass resolution. Here's a mass spectrum from the Cassini INMS. Here's the mass 28 signature. You see here the peak does not have the resolution required to resolve CO from N2. But modern mass spectrometers that can be flown in space, like an instrument at Southwest Research, whose development is being led by Hunter Wade, can easily separate CO and N2. And the same is true for dust mass spectrometers. The University of Stuttgart, Frank Postberg and Ralph Strama have developed an instrument that can separate out amino acids, fatty acids, and identify them. So we want to go back to Enceladus and do exactly what Cassini did. Go into Saturn orbit, fly through the plume, but do it with the mass spectrometers of today, not of 25 years ago. And what we would look for is a whole suite of species that would tell us about the pH of the ocean, the temperature of the hydrothermal systems, the redox state of that ocean, the available chemical energy. And we can look for key indicators of the presence of life. Now, we would not in this mission look for indications of metabolism, because metabolism can be rather specific. But life, by definition, is a low entropy chemical system connected to a higher entropy system. And so low entropy means that the distribution of things like amino acids and fatty acids are different from what you get in abiotic chemical systems. So for example, in meteorites, we see the distribution of these amino acids follows exactly the free energy of formation of those amino acids. The ones that are easiest to form are the ones that are most abundant. But life, the distributions are different. They are what life requires in order to build proteins and sustain living processes. And so it's these kinds of patterns that will stand out dramatically in high-resolution mass spectrometry data from this mission, which we call ELF. Here's Hunter Waite, the deputy PI and lead on the gas mass spectrometer. Frank Postberg, Ralph Strama leads on the dust mass spectrometer. And Linda Spilker is the project scientist, and it is a discovery mission. I want to close, I know I'm late, by pointing out that Europe has been so intimate a part of my career that I could not have done what I have done without it. And a way to indicate that is that when I was a grad student in the 1980s, none of my papers were done with European authors. By the 1990s, 15% were, 2000s, 30%, and the first half of this decade, it's been about 50%. And the three missions that I've been involved in all have substantial European components to them. And I could never have imagined this when I was studying as an undergraduate at Rochester. So here's Jean-Dominique Cassini. I mean, look at everything that he and his name have led us to. Here he is in his younger years, and Cassini today also involves a lot of young people. And this is the Cassini of today. And so here is Linda Spilker, the current Cassini project scientist, US project scientist, with some of the science leadership and some of the mission development team. Yes, very good. People who actually fly the spacecraft. We live in different times, we live in wonderful times, and we only need to keep moving in the direction that we have moved with Cassini in order to address this statement that was made 4 centuries ago by a Swiss physician and traveler, Thomas Plater, who said, "There's so many astonishing things that remain unexplained." Well, let's, in the solar system, go explain them. Thank you.
Thank you very much for this instructive review of the various missions. I learned a lot from listening to it. It's not my subject, but it's really exciting news that you came up with. There's time for probably only one question. We have to leave the room pretty soon. So if there are any questions, yes, please. Please use the microphone up there.
I really love the prospect of finding a different type of life on Titan or different prebiotic chemistry. But I have another question related. There are so many resources on Titan. With just little technology, we could expand our life there. So we heat it up, use these organics, maybe in an artificial environment, not to contaminate the rest. So what is your perspective on how could we expand Earth's life there, but still protecting all the information that we could have on Titan?
So I don't think we should expand Earth life to Titan. There are other places to go. But I will point out that one other advantage of looking for life in the seas of Titan is that we can land there without fear of contaminating that system with the biology of the Earth, because the biology of the Earth is not viable in those seas. Okay, so that immediately eliminates planetary protection concerns. And with ELF and Enceladus, we don't go down into the ocean. We sample the stuff that's been spewed out into space, which is dead already because it's been spewed into the vacuum of space. So both those places to look have a very, very small planetary protection problem. I would say 0. So I think I have time for one more, right? If someone
I think we can take one more.
All right. Nope, they're all either convinced or they've written this off, so fair enough.
Yeah. Okay. But let's thank Jonathan once again for his excellent lecture.